Okay, Organic Chemistry 1. This is the ACS study guide, and we're going to take a look at some multiple choice questions from the ACS study guide. And if you look in the final exam module, you'll see that I posted a list of study guide questions. Some of them are study questions. Those are questions where the study guide actually has a guided solution for them. But we're going to take a look at the practice questions, which do not have a solution for them. So we're just going to figure them out on our own. Now you'll notice that the first question I have in the nomenclature section, and that's where we are right now, we're in nomenclature, is question number 1, but I'm actually going to skip that. We're going to come back to it. We're going to come back to question number 1 in a second, but I actually wanted to start with question number 3. So I think this is a very reasonable question for Organic Chemistry 1. It says, which compound is E,1,2-dichloro-2-pentene? So I think the easiest way to solve this problem is to look for an E compound. Right? I think to look for an E compound is probably the easiest thing to do. And how do we know if something is E or Z, right? E is for entgegen, Z is for zusammen, together. E is opposite or entgegen. Anyhow, so if we look at A, how do we decide whether it's E or Z? We apply the Kohn-Ingold-Prelog rules, which are based on atomic number. So if we look at this carbon right here, okay, you can see that it has a hydrogen attached to it and an ethyl group. Well, the ethyl group is going to be a higher priority than the hydrogen. Now, if we look at the other carbon over here, you see that we have a carbon attached directly here, and we have a chlorine attached here. Well, a chlorine has a higher atomic number than a carbon, and therefore this compound is an E compound. So this is a possibility. If you look at the next one, you can see that this is a Z compound. Why? Because you have the ethyl group and you have the chlorine on the same side of that double bond, and so that is definitely not going to be an answer. I noticed that there's another problem with C because we're looking for a 1,2-dichloro-2-pentene. So if you count the longest carbon chain where you have the 2 chlorines, right? If you were to count this as 1, 2, this would be 1,2-dichloro, but then you have the double bond starting at carbon 3, and so that is not a possibility. If you look at D, same thing. We have 1,2-dichloro, but then the double bond starts at carbon 3, and so that is also not a possibility. What does that mean? That means that the answer has to be E. So let's take a look at it. A. We've already decided that A is an E compound, right? It is opposite or entgegen, okay? Now we just need to check to make sure it's a 1,2-dichloro-2-pentene. So I'm going to erase what I have on there, and let's take a quick look at it. And if you count the carbons, we have 1, 2, 3, 4, 5. We have a chlorine on carbon number 1. We have a chlorine on carbon number 2. And the double bond starts on carbon number 2, and it's an E compound. And so the correct answer is A. So there you go. That's our first problem, is a little bit of alkene nomenclature, which we covered in chapters 7 or 8. I can't remember exactly. But anyhow, let's go back here, and I want to talk about naming this compound here. Now, we didn't look at alcohol nomenclature in Organic Chemistry 1, did we? Okay, but everybody knows what an alcohol is. You all recognize the functional group. There's no other functional group in the compound. And even though we've never gone over the nomenclature of alcohols, you have seen several alcohols like terbutanol or ethanol or methanol, right? And the conjugate bases like methoxide and ethoxide. So let's see if we can use the process of elimination to solve this problem. So you notice that every single suffix is "-al", and that is the suffix for an alcohol. Now, an alcohol is also named like an alkene, and that we want to give the functional group, which is the alcohol, the lowest possible number on the longest chain. So you see that the longest chain of carbons is this one here, and if you circled it going this way, either way, you end up with the exact same answer no matter what. So I'm just going to make a long horizontal line like this, and you can see that in order for this to give the hydroxyl group the lowest possible number, you have to start numbering here. 1, 2, 3, 4, 5, 6. So what does that mean? It means that this must be a 3-hexanol. And so it can only be this answer, right? Because, again, we follow the same kind of nomenclature rule that we do for an alkene or an alkyne, that we want to give the functional group the lowest possible number. And our longest carbon chain has to include the functional group. And then you see that it works out because you have a 5,5-dimethyl here. So alcohol nomenclature is pretty much the same as alkene nomenclature in that we find the longest carbon chain that contains the carbon the functional group, and then we want to give it the lowest possible number, like that. All right. Now, I don't think there's any alcohol nomenclature on your exam, but I just wanted to show you how we can use the process of elimination to solve a problem like this. Well, let's get back to alkene nomenclature and try question number 5. And I'd like to give you guys a second to look at it before we solve it. So it says, which is the structure of Z3,5-dimethyl 3-nonene? I know you can see a little bit of my pencil work on here when I scanned it. I didn't erase it very well. But I'd like you to take a second and see if you can solve this one. And if you think you have an answer, throw it in the chat. Okay, we're getting some answers here. I'll give it a couple more seconds. Just take a quick peek at it. And remember, just if it's your best guess, you just go with your gut, throw it up there. This is a safe space. Feel free to answer the question. You know, okay. There's no judgment. Okay, we're just giving it the old college try here. All right. Okay. Could anybody tell me, and I'm just looking for a short answer, as to why A is not a possible answer? There's no way it could be A. Could anybody tell me why? We can just scratch A off immediately. Say there's no way it could be A. Yeah, okay, okay, perfect. You're all exactly right. You're all saying that it must be a 3-nonene. Okay, that's cool. So you're all saying, yeah, it would be 1,2-nonene. So that's definitely a big problem, isn't it? Okay, so I agree with you, and you're 100% correct. Everybody that answered that. But I say there's another reason. Okay, the other reason is, remember, when you have a carbon of the double bond and the two groups attached to it are the same, right? Those are two methyl groups that I have in those red circles. It can't be E and it can't be Z. There's no E or Z for this compound. So we can scratch that one off right away. If we take a look at B, if we label these two carbons, I'll do one in red and one in blue. Well, if we look at for the higher priority groups on each side, well, the red carbon, the higher priority group is going to be the ethyl group over here. And then the blue carbon has a hydrogen down here, but it also has this big carbon-based group here. So this is an E compound. So it can't be B, right? Because this is an E alkene. And if it's an E alkene, well, that's not a possible answer. If we look at C, if I label this carbon in red and I label this carbon in blue, you can see that the highest priority group on the red carbon is the ethyl group. The blue carbon has a hydrogen up here, which isn't shown. It's a bond line structure, but it has this big group over here, which is on the same side of the double bond as the ethyl group. And so this is a Z compound. But let's just take a quick peek at D, rather. So if you look at D, you see that on the first carbon, we have the ethyl, which is the higher priority. And then on the blue carbon, you have all this, which is on the opposite side. So this is an E alkene. So the answer has to be C, right? It's the only possibility. Now let's double check. Okay, let's take another look here and let's count up the carbons, because our longest carbon chain goes from 1, 2, 3, 4, 5, 6, 7, 8, 9. It's definitely a Z compound. We've already established that. It's definitely a 3-nonene, and we have methyl groups at carbons 3 and carbon 5. So there we go, Z3,5-dimethyl 3-nonene. Give me a thumbs up if you follow me on the rationale for that one. And if you're not 100% sure, feel free to fire a question at me. But does everybody follow me on that one now that you see? Okay, cool. Yeah, so that one we kind of used some process of elimination and some of our, just our prowess of organic chemistry. Look, and you don't have to solve the problem the way I do. I have a lot of students, I've taught organic chemistry for a long time. You know what some students like to do? They say, you know what, Mr. Dion, I'm going to take a piece of scratch paper, I'm going to draw this compound, and then I'm just going to compare it to the 4 answers. Whichever one's the same as mine, that's my answer. And I don't think there's anything wrong with doing it that way. I think that's perfectly fine. Okay, if you just draw the compound out and say which one matches, there we go. Bada boom, bada bing, we're done. All right, now like I told you in the study guide, there's not a lot of questions that deal with Organic Chemistry 1 exclusively. So there's just one more question that I want to take a look at. Question 7. In organic chemistry, we don't look at, or at least in organic chemistry for non-majors, we don't look at an abundance of bifunctional compounds, meaning compounds with two functional groups. This one has an alkene and an alcohol in it, okay? And I just want to show you quickly how you would name a compound like this. Again, it's not, I don't think I have a bifunctional compound on your final exam, but I want to show you how you can apply all the knowledge that you have to be able to solve a problem that might be a little more challenging. And that's the kind of thing that could show up on an MCAT exam or a DAT exam. And again, I know that not everybody in the class is interested in, you know, those kind of exams, but hey, we're all interested in learning. But the first thing I noticed about the names of all these compounds is that they all have the same suffix, right? They all have an all suffix. So that means that must be the way that it's named, right? And they all must be, or the compound must be considered an alcohol. Now, what would we want to do with our functional group? Our main functional group is we want to number the carbon chain in such a way that we give that functional group the lowest possible number. So we're going to go 1, 2, 3, 4, 5, 6, 7. So this is some kind of heptene 2-all. So it's got to be one of these here. And then you have the double bond on the fourth carbon. And so you notice that both of answers C and D satisfy that, right? It can't be A and it can't be B. Okay, so now they both have a 5-methyl too. So all we have to do is decide whether this is an E or a Z compound. Could anybody tell me if this compound is E or Z? And it's not a trick. They're not trying to fool you or anything. Do you guys think this is an E compound or a Z compound? Yep, absolutely. I had to scroll down in the chat. You're all 100% correct. It's a Z compound, isn't it, right? You can see that on the double bond, if I erase some of what's on here, and we just take a look at that double bond, the carbon in green has the ethyl group, and then if I circle this carbon in red, well, that's got this group over here, which are on the same side, so this is a Z compound, and therefore the answer must be D, just like that. So those are some nomenclature problems. And now I want to just move over to the section about structure, hybridization, and resonance, and aromaticity. However, I did not scan one of the questions, so I'm going to go right ahead to question number 3. Okay, so we're going to skip ahead to question number 3. Question number 2 deals with the cyclohexane chair, and we'll talk about that more later on. But question number 3, so I'll give you a second to look at it. It just says, which is an acceptable Lewis structure for diazomethane? And you can see that the condensed structure for diazomethane, since they all have the exact same atoms, right, it must be CH2N2, right? That must be the condensed formula, right, because they all are CH2N2. So it's just a matter of determining, you know, what's the correct Lewis structure. So I'll give you a second to look at it. And the first thing I want to ask you is, could anybody tell me how many valence electrons there must be for diazomethane? This goes right back to your general chemistry days and your organic chemistry 1 days as well. How many valence electrons total would there be in diazomethane? Okay, let's tally up the total number of valence electrons. So for the carbon, right, carbon has, exactly, it's 16. Carbon has 4 valence electrons. Hydrogen has 1 valence electron, and there's 2 of those. So 1 times 2. And how many valence electrons does nitrogen have? It has 5, right? It's in group 5A. So we have 5 times 2. So that gives me 4 plus 2, which is 6, plus 10, which gives me a total of 16 valence electrons. So if you really wanted to do kind of a hammer and tongs approach, you could go around and start counting valence electrons. I mean, there's nothing wrong with that. Let's try it. If we look at A, you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that one has 16 valence electrons. So that's, you know, not unreasonable. So we'll write that down. If we go to B, got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that one also has 16 valence electrons. If we go over to C, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that is impossible. So let's cross that one off. This one has 14 valence electrons, so we'll scratch that out. And then if we go to D, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have an excess of electrons there. So this has 18 valence electrons, and we'll scratch that out. So now it's, which one is it going to be? Is it going to be A or is it going to be B? Does anybody see anything kind of wrong with either of the Lewis structures here? Does anybody notice anything funky about one of them? There's something really jacked up about one of them. No, it's not about having a negative charge on a carbon. Yeah, because we can definitely have a carbon that has a negative charge, right? If you have a carbanion, okay, a carbanion is a carbon with 3 bonds and a lone pair, right? It's got a negative charge, okay? The problem is the nitrogen, right? The nitrogen in A, right? It's surrounded by 10 electrons. Look, it's surrounded by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it's exceeding its octet, which is impossible. So you can't have that as a Lewis structure. Okay, whereas there's nothing wrong with B. Okay, there's nothing wrong with B at all. It's a perfectly reasonable resonance structure, right? This carbon is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons, so it has an octet. This nitrogen is surrounded by 8 electrons, it has an octet, and this nitrogen is surrounded by 8 electrons, it has an octet. So everybody has an octet. The formal charge on the carbon, right, you have 4 valence electrons, subtract 3 sticks and 2 dots, that gives you -1. And the formal charge on this nitrogen, you have 5 valence electrons, subtract 4 sticks and 0 dots gives you +1. So that's reasonable. So there's nothing wrong with B. But again, how did we solve it? We saw we had not enough electrons here, too many electrons here, and then we exceeded the octet rule for the nitrogen in A, right? They had too many electrons. But again, there's nothing wrong with having 3 bonds in a lone pair on carbon, right? That's a carbanion. We see that all the time in organic chemistry. Okay, after that one, let's go take a look at, what was the next one I had? It was number 5. Okay, so let's move down to number 5. So let's go here, number 5. Here we go. I think this is a question that most students would probably nail. I'll give you a second to look at it. It says, which formula is equivalent to the condensed formula here? It's just making a connection between a condensed formula and a partially condensed structure. If you have an answer, just throw it up. Don't be shy. Yep, I agree. Yep. Does anybody else have an answer? Let's give it another second. Yeah, okay. So Kelly says it's D. I agree. Mackenzie says it's D. I agree. I think you're both 100% correct. If we just, and if you're struggling, let's just kind of go at it piece by piece. You see that you've got a carbon that has 3 methyl groups attached to it. So we've got a carbon that's got 1, 2, 3 methyl groups attached to it. So now we've covered this part. Then you've got 2 methylenes. So 1 CH2, another CH2, and then you've got a methyl at the end, like this. Okay, so you have 1, 2, 3, 4, 5. So you actually end up with 2,2-dimethylpentane, which is this compound right here. There you go. All right. I mean, you could tell there's a big problem. Does anybody notice a huge problem in one of the Lewis structures that's just like, whoa, whoa, whoa? Was anybody's eyeball just drawn to something that just said, this is wrong, this does not feel right? I'm just curious if anybody noticed anything totally jacked up. Yeah, definitely, absolutely. You're all totally correct, and it's B, right? I was kind of hoping that, it's always nice to see that at this point in the class, students have seen carbon so many times that they just see that and say, whoa, 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 that is a red flag. Okay, we'll just cross that one out. And then they're kind of like, well, at least now it's down to 3 answers, right? Because B is definitely impossible. And I think that usually students are pretty quick to realize that there's no cyclopropane in here. So you get a cyclopropyl here, right? There's no cyclopropyl. And also in C, there's another problem. Sorry. Yeah, we have a cyclopropyl here and there's no cyclopropyl. So there you go. All right, great work. Excellent, excellent, excellent. Let's try number 6. Okay, so if you remember, and I wouldn't expect you to remember everything I said over the semester, I'm not insane, okay? But if you remember, if you go back to chapter 1, okay, way back in chapter 1, so end of chapter 1, I can't remember if it's section 1.13 or something like that, but anyhow, we covered this question, and I said this comes up every once in a while in this class. It says, what is the hybridization of the orbital containing the unshared pair of electrons on the nitrogen atom in pyridine? And we went over this very specifically, what the hybridization of that lone pair is. Does anybody remember? Yes, yes. It's sp2. Yeah, it's sp2. So if you don't remember why, you can go back and trust me, it won't take you long to go back and refresh your memory. You know, you could read that section in a couple of minutes. But basically, if you look at the aromatic ring, right, and I'll try to draw it the best I can, is since you have the 1, 2, 3 pi bonds, that means that every atom in the ring has an unhybridized p orbital, okay? Even the nitrogen has an unhybridized p orbital, and each one of those p orbitals has an electron in it. So I'll draw one in each one anyhow. And so those all overlap to form a conduit, which is what makes the compound aromatic. And so the lone pair is actually in an orbital that's perpendicular to the plane of the molecule, and that orbital is sp2 hybridized. Okay, so that lone pair doesn't have anything to do with the resonance of the compound, which is kind of interesting. Anyhow, again, it's in chapter 1 at the very end of the chapter. I don't remember exactly which section it is, but if you want to go take a look at that quickly. So excellent work remembering that. It's not easy to remember everything that we cover in class. Let's try question number 7. This is the kind of question that I would expect, you know, most students would probably nail this one. It just says it's got 4 atoms. We've got 3 carbons and an oxygen. And what are the hybridizations? So I'll give you a second to look at it. If you think you have an answer, just throw it up. Don't be shy. And this would go back to chapter 1 as well, hybridization, and a little bit of Gen Chem. All right. Okay, great. I got a couple answers already. I'll give it another second for you to think about it. Yeah. Well, both of my students who answered, I think that they are on the right track. Right. If you remember, yeah, everybody seems to be on the right track. I mean, if you remember back in chapter 1, we talked a little bit about steric number and how to determine hybridization just based off steric number, the number of single bonds and the number of lone pairs. So if we look at atom number 1, okay, it's a carbon with a double bond and 3 sigma bonds and 1 pi bond. So that means it's got a steric number of 3. So that means it's sp2 hybridized. So it's one of these. If we look at the second one, that carbon has 4 sigma bonds. So it's sp3 hybridized. So kind of narrowing it down here really quickly. If we look at the carbon number 3 of the carbonyl, okay, that has 3 sigma bonds and a pi bond. Therefore, it's sp2 hybridized. And then if you look at the oxygen, it's got 2 sigma bonds and it's got 2 lone pairs. So it has a steric number of 4 and therefore it is sp3 hybridized. And so as my student stated, the answer is B. So make sure you review hybridization and you're able to evaluate the hybridization of atoms. Well, if you're like, you know what, I have to go back and review chapter 1. That's no problem. No problem at all. Let's take a look at a question that deals with chapter 10. Okay. And yes, that is my finger in there. I couldn't get the book to stay open. So this is chapter 10, the radicals chapter. It says, for which free radical can the most resonance forms be written that show the delocalization of the radical? I'll just throw that out there to my students. I bet you somebody's got an idea. All right, I think I'm getting some answers here. Okay, so we want to show the most resonance forms. Okay, well, A has no resonance forms. I think we would all probably agree on that. There's no, the unpaired electron isn't allylic to anything, so there's going to be no resonance structures for that one. The problem with B is that, hopefully you remember that I talked about this quite a bit in chapter 10, that there's no vinylic radical. So this is a vinylic radical. Okay, we're never going to see a vinylic radical because there's no resonance forms that can be drawn of it. In fact, it's very, very unstable. So we'll put here unstable. Okay, highly unstable. You'll never see a double bond having a radical on the end like that. That's vinylic. That is very, very unstable. It's just like you would never see a vinylic carbocation, right? Something that we don't see in organic chemistry is this. We don't see a positive charge on a vinylic carbon. So just, oh, where's my eraser? We'll just scratch that out. Whereas if we look at C, C definitely does have resonance contributors. You know, you could start like this, okay? Oops, that's not what I meant to do. There we go. You could start drawing resonance structures like this. So I'll just draw the first one quickly, which would look like this, or we have the double bond like this, and then like this. And then, of course, you could keep moving that unpaired electron around like this, so on and so forth. So C does have 3 more resonance contributors because it is benzylic. Right? This is benzylic. However, D is going to have the most resonance contributors because it's doubly benzylic. Right? This one is doubly benzylic. Right? You can draw resonance contributors where it's going to be down in this ring, okay? And I should say, you can draw resonance contributors where it's going to be over in this ring here. So this one would have a total of 7 resonance contributors, whereas this one would only have a total of 4 resonance contributors. C would only have 4, and D would have 1, 2, 3, 4, 5, 6, 7. Yeah, it would have a total of 7. So the answer is D, because it's got 2 aromatic rings in which you can show the delocalization of the radical. Give me a thumbs up if that makes sense to you. You're like, yeah, makes sense now. All right, cool, good. Okay, let's move on to question number 11. So question 11 deals with resonance. Let me find it here. Question 11, here we go. Question 11. So which pair consists of resonance structures? Let me get the whole thing on here. Okay, we're looking for resonance structures. Remember in chapter 2, we spent a lot of time talking about resonance structures. So we spent a great deal of time in that chapter just practicing our resonance structures. And of course, I know you've all gotten even better at it throughout the course of the semester. No doubt in my mind about that. Let's skip A. Let's go right to B. I just want to throw this out there to my students. Would these two be considered resonance structures? I have trans-2-butene and cis-2-butene. Are these resonance structures? Yes or no? In B. Absolutely, they're not, are they? These are geometric isomers. Geometric isomers. Okay, so these are not resonance structures. If we look at C, these are not resonance structures. You can see that there's no resonance form being drawn here. There's no double bond or anything to draw a resonance. This is, in fact, yeah, it's like Warren says, they're different ions, right? They're actually, you can go from one to the other, but it's not resonance. This would be this is actually a carbocation rearrangement that would occur here. You actually have a ring opening like that, which is a thing, but this is a rearrangement. And so those are not resonance structures. And if we look at D, these are stereoisomers too, right? Just like the geometric isomers, which are stereoisomers. But if you look at D, you have the hydroxyl and the methyl group cis to each other here, and they're trans to each other over here. So these are also stereoisomers. So stereoisomers. But if we look at A, we can draw resonance structures where we show the delocalization of that positive charge. Okay, so let's give it a shot here. And you're not going to be able to go directly between these two, but you can show how you go from one to the other. So let me go back to a blank document here, and I'll show you how to do that. So if we go over here, so this is question number 11, I think. Is that which question it was? Yeah, question number 11. So if we draw this compound, the one that we had at the very beginning, which is this one here, okay, we can draw a resonance structure where we move the double bond up here. So I'm just going to tidy this up a little bit. There we go. Like that. So let's draw this resonance contributor like this, or we've got the double bond here, we've got our methyl group up here, but that's not what was drawn in the study guide. So then we can draw one more resonance contributor where we move this double bond over here because we have another allylic cation. Let's draw what that looks like. And that's going to look like this, where we have the positive charge up here, like that. And there you go. So these are the two that we're given. We're given these two here. I think that the second one is actually drawn as the mirror image, but that's neither here nor there, right? They just flipped the molecule over and they drew it. Sorry. Do I have my double bond in the wrong place? Yeah, I do. So let me fix this double bond. There we go. All right. But they have it drawn like this, which again is the exact same thing. So that means that these two are resonance structures of each other. So somebody asked me about the doubly benzylic radical. So if we go back to that doubly benzylic radical, the one that looks like this, where you have the radical like this, and you have the ring like this, okay? Right, you can show the delocalization of that radical into either ring. So, I mean, you can start here, right, like this, okay? That'll work, and that would give you this, where you have your radical here, and you have a double bond. Sorry, there's a mistake here. Just let me double check something quickly. Yeah, I thought I had an extra hydrogen there, so there we go. So let me just fix this up here. Move that. There we go, like that. So then we have this, like this. Go. Like that. And then you can just keep moving, you know, the radical around. So we'll make a new double bond here. We'll put an unpaired electron there. That's supposed to be a fishhook arrow. There we go. So, I mean, you could just keep moving that around the ring, okay? So, let's draw one more like this. There we go. Like this. Okay. So then we have this looks like this. And there you go. And then you could continue to move that around. But remember, I mean, this is a resonance contributor. So you could just as well, you could take that molecule or you could take that radical. So let me just copy and paste it, right? And you could take that and you could paste it here. Okay, and since this is a contributor, right, you can just draw the resonance structure in the other ring. There's no harm in doing that, right? So then you'd end up with the resonance structure that looks like this. So then you have the double bond here, your hydrogen here, right, like this. You'd have the radical here and here and here. Does that help? Does that clear it up a little bit? All right, we'll go back to the study guide and let's move on. So we looked at that. Doubly benzoic. We covered question number 11. The next one I had was question number 16. Let's move down to question 16. And question 16 was dealing with carbocations, and it just asks us which carbocation is the most stable. So I'll give you a few seconds to look at that. So we're looking for the most stable carbocation. Does anybody have an idea? Okay. So remember, two things you will never, ever, 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 ever see in organic chemistry, okay, is a vinylic or an aromatic radical. So you cannot have an aromatic ring with a radical. You cannot have this. Okay, let me go back to it. There's my aromatic ring that I lost. Okay, you cannot have an aromatic ring, okay, that's going to have a radical. You'll never see that, and you can never have an aromatic carbocation. Impossible. It will not exist. Okay, it's too unstable. So we can cross D out right away. It's impossible. We've never drawn a carbocation on an aromatic ring like that. Okay, if we look at B is primary. It's a primary carbocation, so that's also not going to be very stable, is it? But if we look at A and C, you remember that the position that is directly attached to an aromatic ring is a benzylic position, right? This is a benzylic position. This is a benzylic position. This is benzylic. This is benzylic. This is benzylic. This is. Any group that's attached directly to an aromatic ring is considered a benzylic position. And we also discussed how benzylic carbocations are very stable. Right, so that narrows it down to A and C because they're both benzylic carbocations for which you can draw resonance structures, right? I can move the double bond out here, same thing here. I can move the double bond out here, and I can show the delocalization of that positive charge around the ring, right? You can have a positive charge in a ring if you remove a double bond, right? That's possible, okay? But you're not going to have a double or a positive charge on a carbon that's got a double bond on it. So then the battle becomes between A and C. Which one of these would be more stable because they're both benzylic carbocations? And the answer is going to be A, isn't it? Why would it be A? Because not only is it benzylic, it's also secondary, right? It's benzylic and it's got two carbons attached directly to it. So this is secondary benzylic, and this one over here is only primary benzylic. So remember that R groups or alkyl groups serve to stabilize carbocations through hyperconjugation, and therefore A will be the most stable. So B was primary and D is vinylic, okay, or aromatic technically, but either way, it's not going to be even, it's not even going to exist. So let's move on to the section of stereochemistry. So stereoisomerism is the next chapter. And so we're going to skip this section for now. And we might come back and look at some more acid-base chemistry later on. But I know that stereochemistry is something that if you don't, talk about it a lot, you can tend to lose your stereochemistry prowess. So let's take a look at a question. First question is just 4 molecules. They all have stereocenters. And the question is, 3 of them are S, but 1 of them is R. Could anybody tell me which one is R? And I'll give you a few seconds to look at it. See if you can solve it in your mind. Remember, you'll have scratch paper during your final, as always. Does anybody have an idea which one of these might be R? I'll wait till somebody gives the answer. I'm just going to grab a drink of water. All right, cool. Yeah, let's see if we can just solve the first one as a group. Okay, if we look at A, we have the highest priority group. It's just the oxygen. The lowest priority group is going to be the hydrogen. It's in the back, so that makes it easy. Let's see. Then we have 2 carbons. Well, the carbon that's attached to an oxygen is going to be higher priority than the methyl group. So this is going to be number 2. This would be number 3. So we go from 1 to 2 to 3. We're going counterclockwise, and therefore this one is S. So it's not that one. If we go over to B, we have the hydrogen in the back again, which I always love. It makes it easier. The oxygen has the highest priority. If you look at this carbon, it's attached to oxygen, 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 whereas this one is attached to oxygen, hydrogen, hydrogen. So that means that this one would be carbon number 2. This would be carbon number 3. So I'm just going to erase the rest of this spinach here. So that means we're going which way? We're going from 1 to 2 to 3. Where's my green pen? There we go. From 1 to 2 to 3, which is counterclockwise. So this one is also S. If we go over to D, I'm going to D. I'm skipping C right now. But if we look at D, you see that the hydrogen has lowest priority. So it's number 4. The oxygen is number 1. Then this carbon is attached to nitrogen, 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 and then the methyl group is going to be lower priority than that. So the nitrile will be number 2. This is number 3. So we're going from 1 to 2 to 3. So this is also S. Well, C better be the winner, right? If you look at C, there's no hydrogen attached directly to the carbon, is there? Therefore, you have to go with the lowest priority group, right? You have an oxygen. That's going to be highest priority. This carbon is attached to oxygen, oxygen, oxygen. This carbon is attached to oxygen, hydrogen, hydrogen. And this one is attached to hydrogen, 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 hydrogen. So this one is going to be the lowest priority. This one's going to be second highest, and this one will be third highest. And so we're going from 1 to 2 to 3. We're going clockwise. The lowest priority group is in the back, and therefore this one is R. There we go. So there you go. So this is one where it might be worthwhile to, scribble it down on a piece of scratch paper and see if you can figure out, the stereochemical configuration that way. Let's try another one. Same vein, exact same vein as the last one. I just want to show you one quick thing, which is, I'm going to show you a couple things here. First thing is when you have C6H5, so C6H5, that's the same thing as a phenyl, right? Which is the same thing as this. Right, it's just an aromatic ring. It's just a shorthand for it because it's got 6 carbons and 5 hydrogens. And then if we have a deuterium, right, a deuterium is an isotope of hydrogen, isn't it? Deuterium is a hydrogen with a neutron in its nucleus. So it's hydrogen 2. So since it has a neutron in the nucleus, it has technically a higher atomic number, right, than hydrogen does. So it has a higher priority than hydrogen. So it goes from hydrogen, and then deuterium has higher priority. So if we look at the carbon, I'll highlight this carbon in red, okay? So if we look at the carbon in red, the hydrogen is going to be lowest priority. The deuterium is going to be the third highest priority because it's the closest to hydrogen. Then if you look at the other ones, well, this carbon here is attached to sulfur, oxygen, and carbon. Right, sulfur, oxygen, and carbon. We go with the highest atomic number first. And this one, since it's attached to a phenyl, it's attached to carbon, 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 right? This one is attached to carbon, 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 right? Carbon, carbon, carbon. So that means that this carbon is going to be second highest priority, or sorry, first highest priority. And then the phenyl will be second highest. So we have first highest priority, second, and third, and fourth. So how do we determine the stereochemical configuration here? Because the lowest priority group is facing towards us, isn't it? Right, the lowest priority group is coming out towards us. So we're going to evaluate it, and then we're going to reverse it, aren't we? Right? So let's take a look. If we go from 1 to 2 to 3, like that, we're going counterclockwise, which is S. And since the hydrogen is coming out, we're going to reverse that. So that means the carbon on the left is going to be R. So that means it's either going to be D or it's going to be A. We can cross these ones out. So let's take a look at the carbon on the right. So let me just erase this spinach here. So we'll do this one in blue. There we go. Now, if we look at the groups here, you can see the sulfur is going to be number 1. The oxygen is going to be number 2. This carbon is attached to HHH. Okay, it's a little easier to say. And this carbon is attached to carbon deuterium hydrogen. So this one is going to be the higher priority. So let me just erase this chicken scratch here. So that means that this carbon is going to be third highest priority. And the methyl group is in the back. And it's the lowest priority. So that's kind of nice. So this one we can just evaluate it the way it is. And we go from 1 to 2 to 3 like this, which is clockwise. And so it is R. And so the answer must be A. We're R on the left and we're R on the right. So R for both of them. All right. There we go. Nothing to it. Just a little practice on nomenclature. Stereoisomerism. Let's try question number 5, which deals with something that I know we covered in some detail and it came up from time to time in this class. Where is it? Question number 5. Question number 5, and I'll give you a few seconds to think about this. It just says, which of these molecules, if any, are mesoisomers? So if anybody could identify a mesoisomer, or tell me what the answer is, I guess. So for this one, you'd have to maybe recall the definition of what a meso compound is. Okay, a meso compound, so meso must have at least 2 stereocenters, so greater than or equal to 2 stereocenters, and a plane of symmetry. So there's definitely a plane of symmetry in number 1, isn't there? There's a plane of symmetry in there, but the problem with 1 is that there's no stereocenters in the molecule. Okay, I see a lot of people are saying B, and that is the correct answer. It's only number 2, because number 2, this is a stereocenter and this is a stereocenter, and there is a plane of symmetry that runs down the molecule. Okay, so number 2 is a meso compound. There are stereocenters in C. This is a stereocenter and this is a stereocenter, but there's no plane of symmetry in the molecule. And so the answer is B. Only number 2 is considered a meso compound. Give me a thumbs up if you're like, yeah, I remember now. You know what a meso compound is. All right, cool. Yeah, so it's got to have a couple of stereocenters. It can have more. I'll be honest with you, in Organic Chemistry 1, we never look at examples that have more than 1 stereocenter. Or more than 2 stereocenters, rather, is what I meant to say. So don't stress about that. Like, oh no, how many stereocenters is he going to throw at me? Okay. Let's move on and try question number 7. Question number 7 is a good one. This is a Fisher projection. And again, just asking us to determine the stereochemical configuration of the 2 stereocenters. I'm going to switch over to a blank document so I can write the question out a little bit bigger, but it's just this guy right here. Okay, just this one here. So we've got this would be an aldo tetros is what this is called. So I'm going to go over to a blank document and I'll redraw the compound. So let me just find some space here. So this is question number 7. And let me just scribble it down here for you. So it's got aldehyde at the top. Got two stereocenters, then we got CH2OH. And the two hydroxyls are both on this side, like that. So we've got to figure out the stereochemistry of carbons 2 and 3. So it goes like this. This is carbon number 2. This is carbon number 3. So we'll start with carbon number 2. The lowest priority group is going to be the hydrogen. The highest priority group is going to be the oxygen. If we look at this carbon, it's attached to oxygen, carbon, hydrogen. If we look at this one, it's attached to oxygen, oxygen, hydrogen. So this is second highest priority. This is third highest priority. We go from 1 to 2 to 3. We're going counterclockwise, which would be S. But remember, since this hydrogen is coming out towards you, you reverse it. And so the stereochemistry here is R. So this is a 2R compound. Now I'm just going to erase some of this stuff that's in the way, just to make a little space here for us. So we have a 2R, and then we're going to move on to the next stereocenter, which is carbon number 3. So let's take a look here. The oxygen has the highest priority. The hydrogen has the lowest priority. This carbon is attached to oxygen, hydrogen, hydrogen. This carbon is attached to oxygen, carbon, hydrogen. So this is the tiebreaker. So this would be priority number 2. This is priority number 3. We go from 1 to 2 to 3. We're going counterclockwise again. So that would make it S. But remember, this hydrogen is coming out. So we reverse it, and it's 3R. So it's a 2R, 3R compound. Let's go back here and see if I can find it again through all my scribbles here. Where is it? Somewhere down here, isn't it? Where was it? Good grief, there it is. All right. So it's a 2R, 3R compound. So, something that, you can use as a shorthand that we're going to learn in organic chemistry too, is that when you're looking at compounds like this, not every Fisher projection, but we'll learn some rules. And you'll see that when the hydroxyl is on the right-hand side, it's R. And when it's on the left-hand side, it's usually S. But again, that's something that's covered in organic chemistry too. Well, let's take a look at hydrohalogenation. Okay. What would be the stereochemical classification of the product of this reaction? We have 2-butene. It doesn't tell us anything about cis or trans. That's neither here nor there. Excuse me. And it just says, what do we end up with? A meso compound, a racemic mixture, an R enantiomer, an S enantiomer. It might be worthwhile to try and draw the mechanism of this. But could anybody make a suggestion? And I'll give you some time to think about it. So there's symmetry in the molecule, right? So Markovnikov or anti-Markovnikov doesn't mean anything, but we can still evaluate whether we're going to end up with, what kind of compound we would end up with, right? So if we just draw the structure of HBr, right? When we draw the proton transfer, it doesn't matter if you draw it to this carbon, okay, the carbon on the right of the double bond, or if you draw it to the carbon on the left of the double bond, you end up with the same thing either way, don't you? Okay, you would end up with what? You would end up with this, CH3, CH2, right? You end up with this no matter what. Okay, you end up with a carbocation. Does everybody follow me this far? Making the carbocation, right? And you could draw the bond line structure of it. 1, 2, 3. Like that. So you end up with this carbocation. Now that you know that you have that carbocation, could anybody tell me what type of stereochemical classification we would give to the final product? Right, you end up with a carbocation, which is trigonal planar. This is trigonal planar. So that means that the bromide can attack from either face of the molecule, can't it? So that means that when the bromide attacks, right, it can attack from the back face of the molecule, it could attack from the front face of the molecule. And so what would you end up with? That means that you'd end up with some where the bromide attacked the front face of the molecule, and you end up with some where the bromide attacked the back face of the molecule. So you end up with a racemic mixture, which is also called a racemate. Give me a thumbs up if that makes some sense. If it doesn't, feel free to shoot a question at me. But it's got nothing to do with Markovnikov or anti-Markovnikov addition in this case. This is a chapter about stereochemistry. Right? This question is not asking you about regioselectivity. That would be a question of Markovnikov versus anti-Markovnikov. This is just getting you to understand, well, I'm going to make a carbocation, and a carbocation is trigonoplanar. Therefore, my nucleophile can attack from either face of the molecule. Right? And that's going to give me a racemic mixture of RNS 2-bromobutane. Okay, let's move on to question number, what's the next one? Right over to question number 10. All right, this one, we have some diastereomers. They're all diastereomers of, they're all isomers. Right? You can see that on each one of them, we have a cyclohexane, and every one of them has a methyl group. Right? Every one of them has a hydroxyl, and every one of them has an isopropyl. Right? They all have those three groups on them. Each one of them has the same three groups. Okay, and they're all positioned in the same way. So could anybody tell me which one of these diastereomers would be the most stable of all? Does anybody have an idea? Yeah, it's going to be B. It's going to be the one where everything is equatorial, right? Absolutely. Why? Because that way we have no 1,3-diaxial interactions. All right, you can see in A that we have 1,3-diaxial interactions. They're even trying to show them to you. You have them here. You don't have any in B because everything that's axial is a proton. You have them in C here. And then in D, you have them between the hydroxyl and the methyl. That's really bad. Okay, but in B, everything is equatorial. So all equatorial. And therefore, B is going to be the most stable of all the diastereomers. And so it might be worth your while to review 1,3-diaxial interactions if you need to. Okay, let's move on from there to question number 11. It's another question about stereochemistry. It says the product of this reaction will be achiral, but not meso, a mixture of diastereomers, a meso compound, or a racemate. So you really have to be on your toes with respect to your definitions. You know, what do all these things mean? Is it an achiral compound? Now in this question, Markovnikov and anti-Markovnikov addition does come into play, doesn't it? Would this be a Markovnikov or an anti-Markovnikov addition? Could anybody tell me? Just adding HCl across a double bond. It's going to be Markovnikov, right? And you see that this carbon is the only one that has a hydrogen that's attached to it. So that means the product is going to be this. You end up with this compound where you have the methyl group and you have a chlorine here. That's the compound. So let me just try to draw it a little neater. There you go. So is this going to give you a mixture of diastereomers? No. Let me ask you this. Is there a chiral center in this molecule? Is there a chiral center in this molecule? No, absolutely not. There is no chiral center in this molecule. So this compound is achiral, and it's not a meso compound, because in order for a compound to be meso, it's got to have two or more stereocenters in a plane of symmetry. There's no stereocenters whatsoever. This must be the right answer. If you look at C, it's definitely not a meso compound, and it doesn't have a chiral center. So it's just an achiral compound, right? A meso compound is an achiral compound because it doesn't rotate plane polarized light, but it does have stereocenters, right? Whereas this compound is both. It's achiral and it's not meso. It's just a regular old boring achiral compound. And that's the answer. It's A. And this one, again, is Markovnikov addition. So this time, regioselectivity is important. But I think that most students by this point are pretty good on the whole concept of Markovnikov versus anti-Markovnikov. All right, let's take a look at a question which deals with the stereochemical relationship between two Fisher projections. I'm going to go over this one with you. Again, this is a question that I don't think is on your final exam, manipulating Fisher projections, because it's not tricky, but let me just show you how to do it. It just says, are these two compounds identical? Are they meso? Are they diastereomers? Are they enantiomers? Well, they're not meso because there's no plane of symmetry in either of these molecules, so we can cross that off. Are they diastereomers? Well, are they enantiomers? Well, and are they identical? Well, the thing is you can't take a Fisher projection. Like, say I want to take the first compound, I can't just take it and flip it like this, okay, and then redraw it like this, okay? If you were to try to do that, so you have it like this, so that this is still here, then this would be up here, and then this would be down here. So if you did, and what I'm doing is wrong, so don't think, you could do it, because if you do it that way, then it looks like they're identical compounds. But the problem with this is that the way this Fisher projection is drawn, and the other one too, these bonds are coming out towards you, right? All these bonds are coming out towards you. And so if you flip it 180 like this, then all these bonds are going back, okay? And therefore, you can't compare them that way, okay? So the only way that you can flip the molecule, so to speak, is you can't do that. That's impossible. So we're going to erase all that. What you would have to do is rotate it around a point. So you would choose a point in the middle of the molecule, and you would rotate this end up here, and you would rotate this end down here. Okay, you like spin it around like a top. And then if I spin it around like a top, then what I end up with is this. So I end up with this hydroxyl is being this one up here. This hydroxyl is being this one over here. And then this hydroxyl is going to be this one down here, right? Because now the way that I've drawn it, all these bonds are still coming out like this, okay? So now when you compare the two, you can see that this compound that I just drew and this compound right here are mirror images of each other, right? You see that all the stereochemistry is inverted. This hydroxyl and this one are inverted. This hydroxyl and this one are inverted. This hydroxyl and this one are inverted. And so the answer is these are enantiomers of each other. Now, another way that you could do it, which would be way, way longer, in my opinion, would be if you had nothing but time, you could just sit there and you could evaluate the stereochemistry of every chiral center if you wanted to. And then you'd see that it's, RSR and SRS, okay? But again, that would take way too long to do it. All right, so, really what's this question getting around is that you've got to understand when you see a Fisher projection that the horizontal bonds, they're all coming out towards you. So you can't flip it like a pancake. Cannot do that. It's against the rules. All right, there we go. So let's move on to question number 20. Question number 20. Okay, this is just a word problem. It says cyclohexene. What's cyclohexene? Cyclohexene is this. Take cyclohexane, you add a double bond. We've seen that molecule many, many times. It says reacts with bromine, Br2, to produce 1,2-dibromocyclohexane. Now, what kind of compound do you get? Could anybody tell me, you got a bunch of answers, racemic, and meso. So we see that 2 of the answers say racemic, and 2 of the answers say meso. Could anybody tell me if the bromination, would it occur with syn addition or anti-addition? Does bromination occur with syn addition or anti-addition? And this is a reaction that we looked at many times. And we looked at the mechanism. It occurs with anti-addition, doesn't it? So that means that you would end up with this compound. Let me just try to draw it as neatly as I can. You end up with this compound, okay, plus the enantiomer. Now, there's no there's two chiral centers in this molecule. However, there's no plane of symmetry, is there? Right? There's no plane of symmetry. And so if there's no plane of symmetry, you can scratch meso right out of there. Okay, there's no meso compound here. Okay, now let's focus our attention on A and B. It says racemic, and in the most stable conformation, I'm reading here, they would have both bromine atoms equatorial. And then the next one says racemic, and in the most stable conformation would have one bromine axial and one bromine equatorial. Could anybody tell me which one of these would be a better answer? Would it be A or B? Yeah. Oh, wow. That's great. I'm really happy with how quickly you guys are answering this. Yes. Yes. You're all 100% correct. Everybody that answered, right? Because you know that, let's say, for example, I mean, this has to be down, right? And if this is up, let's say this is down and axial, right? Okay. What would that mean? That would mean that this one is up and axial. So if we back it up and we say if this one is down and equatorial, that means that this would be up and equatorial, wouldn't it? Okay. And so the answer is A, that it's going to be racemic in form. In the most stable conformation, both of the bromines are going to be equatorial. Where's my eraser? There you go. And so that's your answer. Great work. You know, and you can see how in these kind of exams, how they love to ask more than one question at a time, don't they? What did you have to know to answer this question? Many, many things. You had to understand bromination. You had to understand that it's anti-addition. You have to understand the positioning on a cyclohexane ring. Equatorial and axial positions. You have to understand what racemic means, what meso means. So there's a lot of information, as far as I'm concerned, in this question. Not a novice question, okay? Definitely a challenging question where you have to connect a lot of dots. All right, let's take a look at question 21, and I'll give you a couple seconds to think about this one. It just says you got these two compounds. What's the relationship between them? I'll give you a few seconds. Think about it. Does anybody have an answer for 21? Yeah, I would tend to go with C, right? How do we know that? Because if you look at the connectivity in the first one, it's a 1,2 diol, but if you look at the next one, it's a 1,2,3 diol. So they're definitely not identical, right? They're not conformational isomers because the connectivity is different. They're constitutional isomers because they have the same molecular formula. It's just their connectivity is different, and they're not stereoisomers because in order to be stereoisomers, you have to have different connectivity. So we'll put here, connectivity is non-identical, okay? Therefore, they are only constitutional isomers. There you go. So this is a question that I would say would probably be, you know, maybe a little easier than some of those stereochemistry questions that we've looked at already. And for the next one, I made some notes about the next one because there's a lot of information in question 25. It just asks us, you know, you've got cyclobutene in every single one. So cyclobutene, the first one is just addition of water. The next one is addition of HCl. The next one's the bromination. We saw that occurs with trans, produces a trans dibromide. And then this one here, okay? So this is D2 with platinum. So D2 is just deuterium, okay? It's kind of like, let me put kind of like H2. Now, if you're like, well, why would they put deuterium instead of hydrogen? Because you can't leave deuterium out of a bond line structure, right? If I had to draw the bond line structure of butane, I would just draw that. But if I had a deuterium on carbon number 2, you have to put it in, okay? And so the whole point behind having the deuterium is that you have to show, what's the word I'm looking for? You have to show, you know, where the deuteriums are. So what we're going to do is I want to go back to a blank document, and we're just going to go through each one of these one at a time. Why don't we do that? So let me go over here, find some space, okay, and let's just try every single one, and you'll see that we'll be able to figure this one out pretty quick. So we have A. The first one is cyclobutene, and remember, we're looking for a meso compound. So we're looking for meso, okay? So the first one is we're treating it with water and acid. There's no Markovnikov or anti-Markovnikov to consider. All we're doing is adding water across the double bond, so we're going to end up with this. This is called cyclobutanol. There is no chiral center in this molecule. There is no plane of symmetry. There's a plane of symmetry, but there's no chiral center. And so this is not meso. So that is not the answer. If we go to B, I'm pretty sure you guys could answer this faster than me, but you have bromine and carbon tetrachloride. Carbon tetrachloride is just the solvent, but you know that you're going to get anti-addition. So you have bromine up and a bromine down. Plus, you end up with the enantiomer, right? There's two chiral centers, but there's no plane of symmetry. So this is also not meso. The next one is just addition of HCl across the double bond. So HCl. Again, there's no Markovnikov to consider. There's no anti-Markovnikov. So you end up with one chlorocyclobutane. There is no chiral center. So this is not a meso compound. So let me show you what you have to do with that deuterium. Okay, now you know that hydrogenation occurs with syn addition, right? So syn addition. So that means that both hydrogens are added across the same face of the double bond. So this is like a hydrogenation, except you're using deuterium. So it's a deuteration. And so both deuteriums are going to be added to the same face of the molecule. And so you actually have to draw them in. So we'll put them down. And if you drew them both up, that's totally fine. And so here you can see clearly that we end up with a meso compound. And so the answer is D, just like that. All right. And that is the last question in the section on stereochemistry. And the next section that we're going to look at deals with nucleophilic substitution and elimination. So that would be more chapter 7, really would be a major focus on chapter 7. There we go. So let me go back here. And there we go. So we covered all the section on stereoisomerism. So again, the answer, son of a gun, I didn't mean to do that. So again, the answer to this one was, where was the question? This one is the meso compound. And so next we're going to look at substitution and elimination, which is this section here. But I think we've earned a break. And so you could, take a quick look at question number 1, which simply says what reagents could be used to make this compound. So you have 1, 2, 3, 4, 5, 6, 7. So you have what? 2 hexyne is what it is. And the question is just, how would you make 2 hexyne? Which one of these would work? And so when we come back, we'll take a look.